Okay, let's get started. This is the lightning session. You'll hear about each paper for at most 100 seconds. We're going to have the papers in their appearance order in the program, and you can find that order in the program as well as that PDF file. There are no questions allowed, so if you have questions, you'll have plenty of time to ask the presenters later on when they present the paper, as well as during the poster session. I'd like to remind you a couple of things. We're going to run very tight on time, but you are able to vote for the best lightning session talk, as I told you earlier. This is the ballot. It's green, and you know the rules. We'd like you to turn in your vote immediately, right after. There'll be volunteers collecting the votes. And if you don't see anyone, go to the registration desk and place it there. I will be collecting the votes too. And write your full name on the ballot. Do not vote for a paper you're conflicted with, and vote for at most one paper. And you can see the rules. Okay, that's a redundant slide. And this is the conflict of interest rules. So let's get started with the presentations now. There might be from the packets that have not been picked up. Okay. For people who left their ballots in their rooms, we should have some extra ballots in the registration desk. So if you would like to pick it up right away, that should work. But I don't want to delay the session for longer. Control L, right? Okay. You know the deal. Oh, you don't need it? Okay.
Hello, everyone. My name is Lei Jiang. I'm from University of Pittsburgh. Today, I'm very glad to be here to present our paper named Fine-Grained Power Budgeting to Improve Write Throughput of Multiple Level Cell Phase Change Memory. Multiple level cell phase change memory is deemed as a very promising non-volatile memory technology to replace a large portion of DRAM in the future memory hierarchy. However, its write throughput is seriously limited by both chip and DIMM level power constraint. So in this paper, we focus on improving write throughput for MLC PCM. We introduce a global charge pump to balance the power supply among different chips, so our global charge pump can completely overcome the chip-level power constraints. And we also propose a iteration power management, which allocate power token iteration by iteration. So our scheme can better utilize the DIMM level power budget. We can achieve 3.4 times write throughput and improve the performance by 76%. And please come to my presentation. Thank you very much. See you in the afternoon. Thank you.
Hi everyone, I'm Neil. I'll present joint work by Utah and Intel. We all know that DRAM power consumption is a major concern. Recently there have been proposals to use low power DRAM instead of DDR for constructing energy efficient memories, but this does not do much to improve the latency of memory access. Fortunately, there are other DRAM variants, such as Micron's reduced latency DRAM, which provides very fast access to data. But if we were to construct a memory system which uses either RLDRAM or LPDRAM only, then while we would get good performance in the case of RLDRAM, we incur a lot of power overhead, whereas LPDRAM reduces power but loses out in terms of performance. So this motivates the creation of a heterogeneous memory system where both power and performance optimized DRAM paths are used synergistically. One of the major questions to answer while architecting such a DRAM system is to figure out where we shall place data to utilize this heterogeneity. And we observe that in the DRAM, in a cache line, the first word is most often the critical word. And thus, we build our heterogeneous DRAM system such that we fetch the critical word from RLDRAM, thereby providing good performance, whereas the rest of the cache line is fetched from LPDRAM to provide power benefits. Thus, we see a simultaneous system throughput improvement as well as energy improvement. There will be a lot more details at the talk in the afternoon. Thank you.
Hello, my name is Christian Jacobi. I'm with IBM, and I'll be speaking about the introduction of transactional memory, or transactional execution as we call it, into the IBM System Z mainframe. We introduced transactional memory in the CEC12 mainframe, which is, because of that, the first commercially available transactional memory implementation in a general purpose CPU, and it is available since September this year. I will be speaking about the instruction set architecture. I will describe some use cases that we considered in the definition of transactional memory. Very important in the definition of transactional memory is software RAS and debuggability for enterprise computers, as Charles talked about before. I'll describe the concept of constrained transactions, which is a type of transactions that is guaranteed to always complete eventually. I will talk about the actual implementation in the CEC12 CPU, and I will provide some micro-benchmark-based performance results. Thanks.
Hi everybody, I'm Haranjan from University of Southern California. This is a brief trailer of our work, the Warp DMR lightweight error detection for GPU. These days, many supercomputers are powered by GPU. These supercomputers are using GPU to run the scientific computing by leveraging the general purpose computing ability of GPU. Traditionally, GPU hasn't had any error detection schemes because a few pixel errors in the graphics applications are not a problem if those are not perceivable by human eye. But in the scientific computing, even small number of calculation errors are not forgivable. Unsurprisingly, some GPU vendors started to add memory protection schemes to the latest GPU, but there hasn't been any error detection schemes for the execution units, even though the area of the execution unit is getting larger and higher probability of error. So our goal is to design a lightweight error detection method for GPU processing cores. Our work is motivated from this graph. As many of you already know, the GPU's lockstep SIMT execution causes some underutilization issue. So we try to use reuse these idle resources to detect the computation errors. So we categorize the underutilization into two, and we designed two different DMR schemes to leverage each of them. My session will be 1B, so see you later.
Good morning, my name is Damien Hardy, and I will speak about permanent faults and their impact on performance. So, trend suggests that tomorrow failure will not be exceptional, so making hardware perfect will not be scalable. So one solution is to provide processors that operate correctly in the presence of faults by disabling faulty entries. But this will have an impact on the performance. We produce performance variability. Current practice to measure it is to generate fault maps and to run them to get the results. So this may need a lot of computation time, and we are not sure to get accurate results depending on the number of fault maps you use. So what we provide in that work, it's an analytical-based methodology to provide a rapid estimation of the expectation of the performance variability, the distribution without long architectural simulation and without fault maps. So. And it enables designers to determine which structures are more important to protect and to explore reliability-based trade-off. So the session it's in 1B, fault tolerance. Thank you, and I hope to see you there.
Good morning, everybody. I am Andreas Prodromou, and I'm a master's student at the University of Cyprus. Later today, I'll be presenting NogAlert, which is a mechanism capable of providing online and real-time fault detection for networks on chip. The most important outcome of our study is that in networks on chip, checking for legality is the same as checking for correctness in terms of fault detection. NogAlert is capable of providing complete fault detection by checking for illegal instead of incorrect values. The benefit of this is checking for legality is much simpler, and this can lead to extremely fast and extremely efficient fault detection. Fault detection that's real-time, almost instantaneous. And how is this achieved? By using invariance checking, where the inputs and outputs of all the main components are constantly monitored for illegal behavior. Applying invariance checking with NogAlert led to an extremely lightweight solution in terms of area, power, and timing overheads. And also it can scale efficiently to even more complex router designs. So if you're interested, if you want to hear more about this, it's at 2:30, fault tolerance section, and we would be glad to see all of you there. Thank you.
Good morning, everyone. Our paper tackles the question, how should a highly multi-threaded architecture like a GPU pick which threads to issue? And we solve this problem using feedback from the memory system. That feedback is fed and using that feedback, we create a cache-conscious wavefront scheduling scheme. So typically, a thread scheduler will issue instructions from threads as soon as they're ready. This can create an access stream that is extremely bad for the caching system. One possible solution to fix a poor access stream is to ask the cache to fix its cache replacement policy. However, our work takes a different approach. Instead, we use the caching system to detect when a given thread actually has locality and inform the thread scheduler through a feedback mechanism that this locality exists. In response, the cache-conscious thread scheduler actually rearranges the access stream seen by the caching system such that it is much more cache-friendly. So much more cache-friendly, in fact, that the cache hit rate is actually able to outperform Belady optimally replaced caches using other schedulers. And it turns out that the thread scheduler is also happy because this also results in an overall 63% improvement in performance on a series of highly cache-sensitive workloads that we study. So if you'd like to learn more about cache-conscious wavefront scheduling, come see my talk today at 1:30 right here in the Columbia Ballroom. Thank you.
Hello everyone, today I will talk about my Libra paper. The Libra is the unified accelerator for mobile systems. This is basically about what's next after the current heterogeneous system, consisting of the CPUs exploiting IRP and also exploiting GPUs exploiting the DLP. They are still pretty good, but they are not sufficient yet because most of the real applications are not solely favorable to the data level parallelism or not solely favorable to the instruction level parallelism. And rather they are much intermix of the DLP and IRP code region. Therefore, we are proposing the Libra architecture can customize the execution strategy adaptive to the loop characteristics. And the overhead for giving the flexibility can be minimized by removing the expensive hardwares. Yeah, so just come to my presentation just after the previous guy. Yeah, thank you.
Good morning. Today I'm going to talk about some of our recent work that looks at how to make the most effective use of on-chip storage available in a throughput processor, specifically a GPU. Modern GPUs have tens of thousands of threads that all compete for on-chip storage in your system. And so therefore, the amount of storage you can devote on a per-thread basis is very limited. Further, traditional designs take your on-chip storage and divide it up into several different structures. You have a register file that stores thread private values, some programmer-controlled scratchpad memory called shared memory, and storage devoted to caching. So we're proposing a unified design where we take our on-chip memory, we aggregate it into a single logical structure, and then we partition this structure on a per-application basis in the most efficient manner possible. So for example, program A executes most efficiently with a large cache, while program B executes most efficiently with a large register file, and a large shared memory, and a smaller cache. our unified design can improve performance up to 71% and reduce energy up to 33%. Thank you.
Hi, Sudhakar Yalavanchili, Georgia Tech, and Kernel Weaver is a joint project between NVIDIA Research, NEC, and Georgia Tech. And the problem being addressed here is trying to harness the throughput potential of GPUs for data warehousing applications. These applications are typically a mix of arithmetic and relational algebra operators. And arithmetic operators have received a lot of attention in terms of efficient algorithmic implementations on GPUs, relational operators not so much. And one of the problems with these operators is the large data sets that they have to process. Recent data has shown that typical footprints for relational queries in these types of applications, 1 to 50 terabytes. And when you do that, you have multiple data traversals ranging from the host memory up through the GPU memory, up to the memory hierarchy within the GPU. And then these operations are relatively fine-grained. So the amount of investment in data movement per operation tends to be very, very large, and it makes it hard to fully utilize the GPUs. So what this paper proposes is borrowing from loop fusion from classical compiler technology, kernel fusion. Fuse fine-grained kernels, create larger grain computations, enlarge the optimization scope, enhance locality. Kernel Weaver is implemented as a pass within our compilation framework that takes data log kernels, the query language, compiles them for execution on GPUs. The paper is presented in this afternoon session, 3:30, Columbia Ballroom. Thank you.
Hi, my name is Daniel Wang, and the paper I'm presenting is called Night Shift, Scaling the Energy Proportionality Wall Through Server-Level Heterogeneity. So the first thing we look at in this paper is how do you accurately quantify energy proportionality? Historically, the dynamic range has been used to be a proxy of energy proportionality, but in reality, energy proportionality is actually composed of not just the dynamic range, but also something we call the linear deviation. And using the metrics that we were proposed in the first section, we will analyze historical energy proportionality trends. And what we found is that dynamic range improvement has stalled, and in turn, the energy proportionality has also stalled. But there are actually many opportunities to continue improving energy proportionality. We could improve the energy proportionality by lowering the linear deviation. And also, we discovered that there's a large disproportionality at low utilization. So specifically, what we want to do is to target these two, and we introduce our night shift server architecture by basically fronting a low-power compute node with a high-power primary server. And through that, not only do we improve the dynamic range, but also we close the disproportionality at low utilization and improve the linear deviation, resulting in overall energy proportionality improvements. So for more information, we're in session 2B at the British Ballroom today at 3:30. Thank you.
Good morning. My name is Krishna Maladi, and our topic is rethinking DRAM power modes for energy proportionality. So the big problem here is DRAM power is a significant fraction of server power, and it oftentimes is the reason why you see energy disproportionality in servers, because a large component is static that does not scale with the data rate. So the DDR3 is actually optimized for the high bandwidth scenario, which is fine, but the high-speed interface burns a lot of active idle power. And it's also very difficult to power down these memories to deep states, because it takes a lot of wake-up time to be able to bring these to the active state. So if you look at where the major bottleneck is, it's basically in the on-chip DLLs, which are absolutely necessary for correct DRAM operation and timing. But then they're power hungry and also have a large settling time, which means it is impossible to power down these memories without slowing down the applications. So there is no way to win with these power states and long wake-up times. So in our paper, we basically show that to be able to enable these low power modes, we need to have low latency wake-ups. So we can either re-architect the interface to reduce the wake-up latency, or you can retain the interface, power down very aggressively, but then have some techniques to mitigate your performance loss. So we show that with a technique called memlace, which eliminates the DLLs and shifts the timing responsibilities to the controller, you can actually get very fast wake-up for the DRAMs. Alternatively, we also have techniques called memlace and memcorrect, which basically relax your timing constraints and lets you transmit much before the DLL calibration. So in terms of the results, we see substantially better energy per bit and absolutely no performance cost for the DRAMs. We also have a combination of memcorrect and memdrowsy, which gives equally good energy per bit, with less than 10% performance penalty. So in the end, we show you how it is possible to build energy proportional DRAMs using these techniques. I look forward to seeing you in the talk today at 4 o'clock. Thank you.
Hi everyone, my name is Qingyuan Deng, and our work is called CodeScale, Coordinate CPU and Memory System DVFS in Server System. So the motivation of this work is like there are previous work showing that DVFS is a very successful technology to save CPU energy, and we also propose a MEM scale, which is to apply the same DVFS approach to the memory subsystem. We also got some good gain. So now the question is that can we successfully combine those two techniques together to get the maximum gains? Well, it turns out it's not that easy, because uncoordinated DVFS will cause some poor behavior. So we argue that we need some carefully coordinated CPU and memory DVFS to achieve the best results. There are two main contributions of our work. It is the first coordinated DVFS strategy for the CPU and the main memory subsystem. CodeScale also introduced a smart searching algorithm to constrain the search space to good frequency combinations. The main results showing that CodeScale could achieve on average 16% full system energy savings for a wide range of workload. And more importantly, we think CodeScale also introduced a good framework for coordination of power management techniques across different components. Even those techniques are not DVFS. So welcome to our talk. Will be this afternoon. Thank you very much.
Good morning. As we scale processor frequency on the x-axis, the execution time of the running workload goes down with frequency, but the power consumption goes up. So the product of the two, which is energy, has a minimum at some optimal frequency. The processor, though, may be running at a suboptimal frequency, and the goal of our work is based on some execution interval to predict what this optimal frequency is so that we can switch to it in the next execution interval, thereby reducing energy consumption. Well, prior work tried to do this, and let's see how well they did. So here we plot normalized energy savings, starting with the Oracle predictor. Prior work, called stall time and leading loads, seems to be pretty close to optimal, except they were evaluated with a constant access latency memory system. And if we replace this simplified memory system with a realistic DRAM, prior work doesn't do as well. And if we add prefetching, prior work breaks down completely. So when we designed our predictor, we took into account the complexities of DRAM and prefetching. So we do just as well with constant access latency, but we do better with realistic DRAM, and we do much better with prefetching. To find out how we accomplish this, please come to my talk today at 5 p.m. In the section on energy. Thank you.
There's my glitch.
So our presentation is entitled Vector Extensions for Decision Support DBMS Acceleration. To summarize what we did, we profiled a state-of-the-art analytical database engine, and we encountered a lot of potential data-level parallelism there. However, we found that existing SIMD solutions found in modern x86 processor incarnations aren't suitable for capturing this. So our solution proposes alternative extensions. These instructions are more akin to a classic vector architecture with long vector registers and pipelined operations. It's tightly integrated with an out-of-order core and evaluated on a decision support workload. To summarize what we'll talk about, we're going to talk about some of the key issues related to microarchitecture design, such as integrating the vector unit onto the core, scheduling vector instructions out of order. Of particular interest there are indexed memory operations, which is quite difficult to do out of order. We will evaluate and discuss several key experiments presented in the paper. And to summarize performance, we're seeing speedups over the scalar baseline between 1.9 and 4.5 times for 41% of a decision support benchmark. Thank you.
Hello, I will be highlighting the main contributions of Knockout Microarchitecting a Scale-Out Processor, which is a processor that is optimized to run scale-out workloads, like media streaming, social networking, or web search. Scale-out processors need to have many cores and provide fast access to the last level cache. Our prior work established a methodology for deriving the core and cache building blocks of scale-out processors. In this work, we provide an organization for the processor. We show that existing tiled organizations are not well suited for scale-out processors. We argue for specializing the chip organization to maximize efficiency. We propose Knockout based on one simple observation. This observation is that there is almost no core-to-core communication in scale-out workloads. Based on this observation, Knockout decouples cores and the last level cache, eliminates all core-to-core links, and uses specialized tree-based networks to connect cores to the last level cache and vice versa. The bottom line is that Knockout delivers the performance of the state-of-the-art with 1/10 of the area. Hope to see you all tomorrow at 9 a.m. Thank you.
Hello, everyone. So we're talking about online transaction processing, or OLTP, which is a very important workload in a multi-billion-dollar industry. OLTP's performance is known to suffer from lots of instruction stalls due to first-level instruction misses. They're formed of many concurrent transactions where each transaction has an instruction footprint that is several times larger than the L1 cache size, thus incurring cache thrashing. CMP integration results in an aggregate L1 cache capacity that is several times larger than a single core. Thus, we can exploit transactions to utilize this capacity by distributing their code segments across multiple cores and scheduling the transactions accordingly. So Slick dynamically divides the instruction footprint into smaller code segments where each segment fits in an L1 instruction cache, then spreads these segments across multiple cores, and Slick then schedules transactions in a way that transactions chase after the desired code segments, boosting instruction locality and reducing overall miss rate. So Slick, by evaluation, Slick shows that it can reduce instruction misses significantly, resulting in an overall performance improvement. So my talk is tomorrow, session 3A, 9:30 a.m. in this room. Looking forward to see you all. And you might guess what this figure is. Thank you.
Hi, everybody. I'm Ramon Bertran, and tomorrow I will talk about systematic energy characterization of processor systems via automated micro-benchmark. The problem here is that current processor designs are so complex that makes it difficult to answer questions like, do we have power, thermal, or inductive noise issues in our design? Do we have any performance back, or do we have any reliability issue? Answering to these questions is very difficult, and the design team has to do it during all the design process, from early stage, pre-silicon, to post-silicon stage. In this work, we take the position that automated micro-benchmark hold the key to answer to these questions. We propose MicroProbe, a micro-benchmark generator framework that systematically helps to systematically generate this specifically targeted micro-benchmark. MicroProbe works as following. It takes as input micro-benchmark generation policy and architecture definition. Then it automatically generates the micro-benchmark requested, and if needed, external tools are used to evaluate the solutions. Tomorrow I will talk about how we use MicroProbe to solve 3 energy-related issues, such as generating training sets to produce more accurate power models, to perform instruction-wise API characterization, and to generate automatically max power stress marks. Thank you very much, and see you tomorrow on my session. Thank you.
Hello, my name is Youngtaek Kim. Tuesday 9 a.m. I will present on automation framework for stress mark generation. Audit generates effective DIT stress mark in a short time, and audit works well with different configuration and different architectures. There is a important reliability issue in a microprocessor. A rapid current change can make voltage fluctuate, and if it repeats and meets a certain frequency, voltage will resonate, and supply voltage may go beyond the voltage margin. If the insufficient voltage situation happen, we could get wrong results, OS freezing, blue screen, or sudden system shutdown. So to analyze the DIDT problem, we used real hardware measurement. And audit-generated stress mark has larger voltage group and higher failure point compared to standard benchmark and other stress mark. Thank you.
Hi. In this work, we report the new IBM Power 7 Plus processors power proxy. I know there's a lot of P's in this sentence. This work has the following novelties. First, we present a full methodology with a combined hardware and firmware approach. We are able to achieve competitive accuracy with a much faster reporting rate. And those power proxies, they are adaptable to significant process variations and across the full range of voltage and frequencies. And for the first time, we also decouple voltage and frequencies in the model instead of using fixed voltage and frequency pairs. We also use simple model formula with physical meanings, and the entire methodology is flexible enough to account for new things such as on-chip VRMs and core-level voltage islands. To highlight, on the right-hand side, is a fixed frequency run for DO2, and we start at a relatively high fixed voltage, and at some point, we enable a very cool feature of Power 7 Plus, where the hardware is able to monitor every core's available timing margin on the fly and reduce voltage as necessary to reduce power without hurting frequency. So as we can see on the left y-axis, this amount of power proxy that we have, it tracks really well to the real VDD rail power measurement across all the 32 millisecond measurement. Okay, that's all I have. Thank you.
Hi, my name is Moin Qureshi. This work is about DRAM caches, how to architect large and fast DRAM caches, and this work is done with Gabriel Lowe of AMD. 3D stacking can provide hundreds of megabytes of cache. The problem with such a big cache, how to design a tag store. For example, if you have a 256 megabyte cache, you need about 20 megabytes of tag store. You can't place it in SRAM. It'll be too big. It's fast, but too big. And people thought that this is the upper bound. Another way is to store the tags in DRAM, but that is slow because you have to first access the tag, then second access will get the data. A recent work reduced this latency from 2x to about 1.5x by placing tags and data in the same row, so roughly 1.5x. But similar to prior work, DRAM caches have been architected similar to SRAM caches. High associativity, intelligent replacement, all of the good things that we have been doing for the last 25 years. What this paper is about is actually unlearning a lot of those things. DRAM caches are different than SRAM caches. They are slow. They are about half the latency of memory. And to design such caches, if we just take all of the existing optimizations and put in, they don't work. For example, what is better? Random replacement with lower hit rate or intelligent replacement with higher hit rate? For SRAM, you'd pick this. For DRAM, actually, this makes sense. Does set associativity matter? actually direct map caches makes more sense. To give you the key result, for the low-end hill cache, you get about 8% performance. With SRAM tags, you get about 24%. And people thought that this is the upper bound. The new cache design gives you about 1.5 times of that, 35%, and it only requires a 100-byte predictor. Thank you.
Good morning. My name is Jae Young-shin from Georgia Tech. Our work is in the context of DRAM caches and addresses the inefficiencies of the current DRAM cache. The first one is a cache line tracking structure called mismap. Mismap requires 4 megabytes storage for 1 gigabyte DRAM cache, so it's almost impractical. The second one is underutilization of system bandwidth. This is because we operate the DRAM cache as the conventional SM cache. To solve the first problem, we replace mismap with a low-cost heat predictor. Our heat predictor are based on the region-based, so that it's completely different from the previous conventional history-based predictors. For the second problem, we dynamically steer heat requests to object memory if it's faster. Both solutions can lead to incorrect executions because of dirty data. So to solve this dirty data problem, we maintain a mostly clean DM cache using dirty vision tracker. This dirt enables a hybrid write-through and write-back policy for DM caches. Our results shows that our combined solution improved performance more than 20% over the baseline, and so that they can be practically used in the commercial products. My talk is tomorrow. Thank you.
Good morning. I'm Bing Pham from Rutgers University. So today I'm going to talk about code, which is a hardware technique used to improve the performance of the TLB. So TLB stands for the translation look aside buffer. It is used to cache mapping between virtual address and physical address. TLB misses have been known to decrease system performance from 10 to 15%. So our work is relying on the notion of contiguity, which is mapping between consecutive virtual pages to consecutive physical pages. We see that if a system has high contiguity, for example, the one shown in the diagram, where we have 512 consecutive mappings, the OS can construct a super page, and in return, a single TLB entry can be used to keep all these mappings. On the other hand, if a system has low contiguity, which is shown in the yellow color, TLB organization change or refreshing can be used to improve performance. But even in this case, a standard TLB with 4 entry cannot use to keep all these 5 mappings. So we observe that there exists intermediate contiguity transparently generated by the OS that we can leverage and design a low overhead core-less TLB. So with the same example, we can just use 3 entries to keep all these 5 mappings, because the 3 contiguous mapping from 514 to 516 can be collapsed into a single entry. So details will be discussed in my presentation tomorrow, but as a heads up, this technique can be used to eliminate from 40 to 50% TLB misses, translate to 14% system performance improvement. So thank you, and I'm looking forward to seeing you tomorrow.
Hi, I'm Li Zong from the University of Southern California. So this work is about effective power gating of on-chip routers. So power gating is a promising technique to reduce the static power, but there are 2 major problems when we apply it to on-chip networks. First, the packet arrivals in the on-chip network are quite intermittent, which breaks the long idle period into fragmented intervals, which are too short to be exploited by the power gating. And second, whenever packets encounter powered off routers, it has to wake up the routers and wait for it. So this causes large performance penalty. And in this work, what we propose is a called node router decoupling, which breaks the dependence between the node and the router through a decoupling bypass. So even if routers are powered off, packets can still be transferred using the bypass, and thereby avoiding both the energy overhead in waking up the routers as well as the performance penalty. And we also design a routing algorithm that is deadlock-free under the presence of both on and off routers, and we also exploit the difference in the router locations in the NOC to further increase its efficiency. And I hope you will come to the talk to understand more about this node router decoupling idea and see how much power savings it can achieve. Thank you.
Well, good morning, everyone. As some of you are aware of, there is an increasing gap between the interconnect power and the power it takes to perform a op. And if this power is not taken care of, it can significantly increase the overall performance of a microprocessor. One potential disruptive technology is nanophotonics, as it provides a lower energy per bit compared to electronics and increased bandwidth due to properties such as wavelength division multiplexing. Furthermore, due to increases in technology, it's now capable to have multiple optical layers, and this allows for increased bandwidth density and a unique ability to do reconfiguration. And we do reconfiguration totally optically using optical vias, which are more or less stacked microring resonators on top of each other, which allows the light to go from one layer to another. And combining these two technologies, disruptive technologies, we see about a 23% improvement in power, decrease in power compared to flat and butterfly, and a 36% decrease in power compared to the mesh network. And I will see you tomorrow at the Interconnect Section 4 from 10:30 to 12. Thanks.
Hello everyone, this is paper number 26. Our work is targeting NOC-based multi-cores. Specifically, we analyze the contribution of network on chip to the end-to-end memory access latency. Well, we know that an off-chip memory request must travel through the NOC until it reaches the memory controller, and then the corresponding response message must also travel through the NOC until it comes back to the core that initiated the request. In our paper, we first analyze and show that the contribution of the NOC to the end-to-end latency can be quite high. And then we show that there can be significant variations in this latency. And packets, the messages that are delayed, can block the instruction window on the cores and in turn degrade the performance of the system. We propose two schemes to address these issues. The first one coordinates cores and the memory controllers to identify which messages are late. And then we use prioritization at the routers for these late messages to reduce the network on chip latency and provide a more uniform latency. Our second scheme uses network prioritization, but this time for a different purpose. It expedites messages targeting idle banks to improve memory bank utilization. Overall, our experimental evaluation shows that we can reach 10 to 15% performance improvement. Moreover, we also show that our improvements increase as we put more number of cores into the chip. Thank you.
Hi. Can we design a core microarchitecture that adapts to thread-level parallelism in programs? Yes, Morph core. Morph core provides high performance and energy efficiency on both single-threaded and multi-threaded programs. Morph core is opposite of previous proposals. First, the base design is large out-of-order core. Then we add in-order SMT. It operates in two modes. In out-of-order mode, it operates as an out-of-order core to exploit ILP, resulting in high single-thread performance. In in-order mode, it morphs into a highly threaded in-order SMT core to efficiently exploit the available thread-level parallelism, resulting in high multi-thread performance. Since no out-of-order execution is done, it saves energy as well. By requiring only minimal changes to a traditional out-of-order core, Morph core outperforms 2- and 4-way SMT large out-of-order cores, medium out-of-order cores, small in-order cores, and core fusion. Here is the title of my talk and my co-authors. See you on Tuesday at 1:30 p.m. in Section 5A on core design. Thank you.
All right, my name is Andrew, and I'm from the University of Michigan, and I'm here to talk about composite cores. So one of the big challenges in trying to design heterogeneous systems is that there is a lot of state associated with each engine. So the top is an out-of-order core, and the bottom is an in-order core. And when you want to switch between the two, you end up having to transfer a bunch of state. And this limits the amount, the frequency at which you can switch between these two. So what we want to look at is, what if in fact you squish the two together by basically adding a shared front end and combining the data caches so that basically all you have to do when you want to switch cores is transfer a much smaller amount of state back and forth. And this should allow you to switch back and forth more frequently. And the question is, what does that get us? So if you use a 3-wide out of order as your big model and a 2-wide in order as a little, and you're willing to allow a 5% performance loss relative to an all big, traditional kind of large overheads, OS-based scheduling algorithms can only spend somewhere around 25% of the time on the little. But if you can actually schedule at a much finer granularity, you can end up spending much more time on the little core or the little backend at the same level of performance. So there's more details coming tomorrow afternoon. Thank you.
Good morning. My name is Rami Sheikh from NC State University. Our paper is titled Control Flow Decoupling. Our work targets limitations of state-of-art branch predictors. We found that a third of the mispredictions in 4 benchmark suites come from what we call separable branches. A separable branch guards a large control-dependent region, which makes if conversion not profitable. What we observe is that the control-dependent region in many of this class of branch doesn't feed back into the branch slice, making the branch slice and the branch and control-dependent region separable. We propose our novel idea, control flow decoupling, or CFD. The control flow decoupling transforms this original loop into 2 loops that are fetched serially to preserve the simple sequencing model of superscalar processor that is a single thread in order fetch. The first loop contains the branch slice, or all branch slices, computes the branch predicate, and pushes the predicate onto an architectural branch queue that resides in the instruction fetch unit. The second loop contains the branch and the control-dependent region. We pre-compute all branch predicates, generating a vector of predicates, then we consume it in the second loop, providing timely, non-speculative branching in the second loop. CFD is a hardware-software collaboration that exploits the separability property with low complexity and high efficacy. It delivers performance gains up to 43% and energy savings up to 41%. We automated CFD in the GCC compiler, and we show that it is as applicable as if conversion, a technique that exists in commercial ISAs. And I look forward to seeing you in my talk tomorrow in the core design session at 1:30. Thank you.
Hello, my name is Mohammad Ali Safai. The paper I will present in this micro is spatio-temporal coherence tracking. In this paper, I use spatial and temporal properties of data to reduce the size of the coherence directory. This is an important problem because in CMPs, coherence directory consumes a large fraction of on-chip area at a high core count. I observed that although data is accessed by many cores during the entire application execution, at each point of time, a data region is accessed by just one core. I call such data regions temporarily private because they look like private data to the cores that are accessing them. Based on this observation, I designed a dual-grain coherence tracking directory. It maintains coarse grain coherence information for temporarily private data, and for shared data, it maintains fine-grain coherence information. Since majority of regions are temporarily private, this approach achieves a huge reduction in the directory size. And since it provides support for fine-grain sharing, it also provides a good performance. Compared to a directory that only maintains fine-grain coherence information, this approach can reduce the required storage size by 75% while delivering almost the same performance. Please come to my presentation to know more about this work. Thank you.
Hi, my name is Socrates Dimitriadis. I'm a PhD candidate at the University of Pittsburgh, and my work is titled Predicting Coherence Communication by Tracking Synchronization Points and Runtime. So the key contribution of this work is the proposal of synchronization point-based prediction, which is a new runtime approach for predicting coherence request targets. The approach builds on the intuition that inter-thread communication caused by coherence transactions is tightly related with the synchronization points in parallel execution. And the main idea here is to associate the communication behavior with synchronization points and use this to do effective predictions. The SP prediction exploits communication localities based on application-defined variable length execution intervals, and it has very low storage costs and resource usage compared to traditional address and instruction-based prediction approaches, yet delivers relatively high performance. It takes also advantage of the existing programming paradigm while being transparent to the programmer or the compiler. So in my talk tomorrow, I'm going to briefly go through what is coherence communication and why prediction is important. Then I'm going to show you how synchronization points are related to the communication behavior and what are the new prediction opportunities. Then I'm going to describe how SP prediction exploits the new opportunities to predict the coherence communication targets. And at the end, I'm going to show the results that show how effective is SP prediction and how it compares to other general prediction approaches. The talk is tomorrow after lunch, and I'll be happy to see you all. Thank you.
Good morning. This talk is Vulkan, hardware support for detecting sequential consistency violations dynamically. So what is sequential consistency violation? What you have here is I allocate a variable, I set a flag, I test the flag, and then I access the variable. Everything is fine except that the stores complete out of order. So what happens then is that the flag is set, then you check the flag, you access the variable, and then it's not allocated. So this crashes the code. So in a sequential consistency violation, memory accesses get reordered unintuitively, virtually always a bug, and it happens quite often. So what's the idea of our scheme? If you look at what an SCV violation, SCV requires, is you need 2 data races at least that overlap in time. So you see Y's and X's here. And also they create a cycle, which means that, I don't know if this works, that this one happens before the other one, and the one below happens before this one. So that's precisely what Vulkan does. What Vulkan does is it has hardware to check the order of dependencies across threads. And it uses cache coherence protocol transactions. And whenever it detects one, it has an exception, and the debugger can debug this very hard to debug bug. So what we found is we can detect sequential consistency violations precisely. We found 3 new bugs in codes such as libraries, very common. No execution overhead. We can use it on the fly, and we don't need any software changes. Thank you.
Good morning. I'm going to be talking about the amoeba cache and how we eliminate waste in the memory hierarchy using adaptive granularity cache blocks. Here is a look at a fixed granularity cache where the data accessed by the application during the lifetime of the block is highlighted. As you can see, there is waste in the cache blocks as demarcated by the black blocks. Now let us imagine that if we were able to eliminate this waste, we end up with a non-uniform structure, as you can see on the right. Now, in order to store precise information regarding this structure, we need extra metadata in the form of more tags. Also, the sets themselves are no longer equal in size. The 2 key questions that we need to answer over here are, how do we support a variable number of blocks per set, and how do we support variable granularity within each block? Our approach is to collocate the tags and the variable granularity data into a single unified SRAM array. Our target metrics are bandwidth, miss rate, and space utilization, and the amoeba cache attempts to improve on all these. Our results show that we improved the L1 and L2 miss rate by 18%, on-chip bandwidth by 46%, off-chip bandwidth by 38%, overall energy by 11%, and improves performance by 10%. My session is on Wednesday morning at 10 a.m., and I look forward to seeing you all there. Thank you.
Morning, my name is Nam Dung. I'm from UCLI. Our paper is about improving cache management policies using dynamic reuse distances, and we target large level caches. So in this paper, we propose a new cache replacement and partition policy with a better balance between reuse and pollution. So the balance states that cache lines must be kept long enough to be reused. However, if the lines are be kept too long without reuse, it's going to pollute the cache, so that the performance is impacted. We introduced a new concept, the protected distance, that is based on the reuse distance, balancing the reuse and pollution. And using the protected distance, inserted line cannot be evicted for PD access until the PD access to the set, and this can be guaranteed if the cache bypass is also used. And we developed single and multi-core single model, hit rate models as a function of the protected distance, the cache configuration, and the program behavior. This model, this model is shown to accurately predict the future behavior of the cache, and it is used to dynamically compute the protecting distance. And we show that PD-based management policies improve performance over single and multi-core system. So if you are curious about the graph, please come to my sessions. Yeah, thank you.
Hello. The core of the problem that we try to solve is how to optimally partition the graph. Means you have your graph, you have your scissors, and how to cut this graph into different subgraphs in an optimal way. You can say, well, this is easy. This is an old problem, and there are so many heuristics-based solutions that can give you a good partition. And this is correct. However, even today, we don't know how good these heuristics-based approaches are. When I say how good they are, I'm thinking, what is the performance difference between the solutions they provide and the optimal graph partition? The reason for this is that graph partitioning is interactable, NP-complete problem. So we cannot know what the optimal partition is, nor we can know its performance. Our idea is to statistically estimate the performance of the optimal graph partition. In order to do so, you will have to run number of random graph partitions, measure their performance, and then statistically estimate the performance of the optimal solution. This not only proves the evaluation of any heuristic-based approach, but our paper also shows how random sampling on its own can be a solution to your problem. If you're interested how we apply this to problem of kernel partitioning for streaming applications, please visit us during the poster session or during the 30 minutes presentation. Or we can always have a coffee. Thank you.
Right, good morning. My name is Ben Lee. Unfortunately, Wei Dan couldn't make it. We'll be talking about inferred models for dynamic and sparse hardware-software interfaces. We're really motivated by a particular challenge, which is mapping software to hardware. In complex systems, we're seeing increasingly heterogeneous hardware, and we're also seeing increasingly diverse software. Think cloud computing. Now, we're going to try to map these software tasks to hardware, but we're going to find that there are quite a few possible hardware-software mappings we could perform, and this management space explodes very rapidly. What we might do to address this problem might be to infer with sparse profiles. If you have a sparse profile running in your cluster, you can measure the performance of these various characteristics and perhaps infer the performance characteristics of all the other possible mappings. This integrated hardware and software approach lays a foundation for runtime management,
and we exploit increasing diversity among our sparse samples, and we differentiate ourselves from prior work because which separated the hardware-software analysis, whereas we integrate the two. Our principles and strategies here are to enhance data reusability. And this means looking at short instruction segments, shards we call them, and measuring portable characteristics that are independent of the microarchitecture. Moreover, we can accommodate dynamic systems that evolve over time. Maybe new machines enter the system, maybe new applications enter the system, and we have an automatic genetic algorithm that can train and update the model. This model is accurate. We can predict the performance of various characteristics and extrapolate beyond the applications and architectures we've seen within 5 to 10%. Thank you very much indeed.
Hello, I'm Chen Wang, and I'm talking about the software-managed alias register queue. Previous work used the alias register for data speculation in two different ways. One way is the software-managed alias register file. Another way is the hardware-managed alias register queue. And the software-managed alias register file is used for software speculation on in-order CPU. Two examples are Itanium and the Transmeta processor. Unfortunately, the Itanium approach suffers from a false positive issue, and the Transmeta alias register cannot scale up to a large number of alias register number. And the hardware-managed alias register queue is widely used in hardware speculation on out-of-order CPU. Without software analysis, it suffers from the efficiency issue and cannot be used for general software optimization. In this work, we combine these two approaches. We get a smart queue, software-managed alias register queue, which take advantage of both. In order to achieve that, we need to leverage novel architecture features and a compiler algorithm to solve all the issues in previous work. And all experiment with a dynamic optimization system on an in-order processor shows that on average we can get 39% speed up with software speculation. And we also see 13% of the speed up come from the fact that smart queue don't have false positive. And on average, 10% speed up is due to the fact that smart queue can scale up to a large number of alias registers. Welcome to my presentation on Wednesday for more details.
Hello, my name is Alan. My paper is about profiling data dependencies to assist parallelization. It introduces a tool called ParWiz, which is a parallelization assistant. You give it a sequential executable, a set of representative data, and at the end of the run, you get hints on where the parallelism is and what you can do about it. It works by just tracing memory accesses, collecting data dependencies with elaborate descriptions, attach them to program structures, and then use any kind of generic decision or parallelization algorithm. We've used this for various applications, ranging from loop parallelism to finding vectorization opportunities. There are 3 use cases in the paper. You get another one if you come see my poster, and I'll describe yet another one on Wednesday morning during my talk. That is all well and good, but the problem is that it's slightly time-consuming, and we cannot use sampling in that case, so it's way too inaccurate. So we have the idea to use static analysis on the binary code to avoid unnecessary memory access instrumentation. So this probably applies to other kinds of memory tracing tasks, but in our case, we just save 1/3 of the time for this. So thank you. See you on Wednesday morning.
Hi, my name is Adrian Sampson, and I want to talk to you about work at the University of Washington and Microsoft Research on accelerating approximate programs using neural networks. This is founded on some recent work that shows that lots of programs, lots of today's most important programs, are soft, which means they have built-in tolerance to errors. They don't need all the correctness that hardware currently provides them. These kinds of applications are things like voice recognition, augmented reality, search. All these things can tolerate errors, and we can exploit that to improve energy and performance. The central observation of this work is that neural networks can efficiently approximate functions within programs that are written traditionally, using traditional programming languages. And this works by asking the programmer to annotate certain functions within the program that are approximable, extracting those from the program, training a neural network to replace the original function, and replacing the original code with an invocation of an extremely efficient hardware neural network that we call a neural processing unit that's tightly coupled with the core so that we can even accelerate very small code regions. We simulated 6 different approximable benchmarks and see that we have a 2.3x average performance improvement and a 3x improvement in energy consumption over the entire application. All this comes at a cost of less than 10% in the output quality of each of these applications. My talk is in the very last session on the very last day, so please stick around. Thanks.
Thanks. I'm Jan van Lunteren. Our talk is dealing with the design of a programmable regular expression. I'm losing some seconds here, I guess. Sorry. This is a regular expression accelerator and compiler with the objective to support thousands of regular expressions in parallel at wire speed scan rates on the order of 20 gigabits per second, while also providing support for millions of active sessions and incremental updates. The design challenges in our case focused or centered around the memory system. In particular, we had to deal with something called state explosion problem, which is a well-known issue in this field. There were also some other latency-related things we had to deal with as well. Oops. So we came up with an architecture that we built from programmable state machines in combination with simple, fast processing elements and a software-managed level 1 cache. And all of this was provided as a kind of, or programmed in a kind of a RISC style of fashion. Also, the architecture provides all kinds of dispatch and executions options that were flexible enough for us to allow making our performance targets. The accelerator has been implemented as part of a larger SoC design in 45 nanometer technology, clocked at 2 to 3 gigahertz. It was able to deliver a peak scan rate of 73.6 gigabits per second. For typical network intrusion detection workloads, we measured on the actual hardware scan rates in the range from 15 to 40 gigabits per second. Thanks very much.
Okay, that brings us to the end of the lightning session, and we're on time. And I'm very happy, and I'd like to thank the speakers that I didn't have to use this. You can take some time to actually make a decision on the best lightning presentation you've seen, but by the time you leave this room, please make sure that the ballot is at the hand of the volunteers in the back. I will be one of those volunteers. But before that, let's thank all of the speakers again. And we'll have lunch after this. Where? It's at the ballroom. Oh, Pacific Ballroom. And we'll start the next session at 1:30. And it'll be parallel sessions, this room and the room next to this. Thank you. Oh, if you're a speaker in the next